do something a little different. I usually do videos in Mathematica, but I'm going to use Geogebra, which is a fantastic tool to help us visualize mathematics. We're going to use it today to illustrate linear transformations through matrix multiplication. Alright, so if you're in my class, you have this document. This is our Geogebra Transformations lab. Make sure that you follow along this video with your document, and I'm going to walk you through it step by step. If you're not in the class, you feel free to use this document as well. I'll provide a link to it in the description below. But again, I'm going to walk you through every part of this. Okay, now Geogebra is very friendly. I'm using the downloaded app. You can use the browser app if you want. It'll look a little different, but the concepts are still the same. We have, you can see here, a geometric space, and then over here we have what we call the algebra menu down on the side here. So if I click point, for example, and this is the first thing you want to do, I can just drop points in the plane, and as I drop them in, they show up in the algebra list as with the coordinates. And if I click the move tool, I can move around those points and notice the coordinates update in live time, which is pretty cool. So the first thing we want to do is just drop some points in the plane, and I want you to use at least 5. You can use maybe up to 10. The more you put in, the more work it's going to be. I'm just going to put in 7 here. And then I'm going to go to the polygon tool and just connect these together to make some sort of shape. Okay, so notice when I complete that, a lot happens over here in the algebra menu. I have a location for each point. I also have the polygon named poly, and then each segment on the polygon has a name to it as well. Now, if I wanted to, I could come in and change the settings for each of my objects here. I could take off the label if I want. I can change the color of my polygon, for example. Maybe I want a nice blue color, and you're free to do this how you want. Okay, so the next thing we want to do before we get started with any of our linear algebra stuff is we want to type in a matrix that I'm just going to call matrix with a lowercase m. And the way I put in matrices in GeoGebra is just like I would in Mathematica. It's just a list of lists. So in the first list I have 1, 0 for my first row, and the second list I have 0, 1. That matrix is going to show up at the top, and this is just the identity matrix. And we're going to use that later on. Part 3 of this is that I'm going to go to my lines tool and find vector, and I'm going to draw vectors stemming from the origin to every single one of my points. So the more points you have, the more vectors you're going to need. And there they all are. Now you can tell in the algebra menu, you want to verify that each vector is identified as a vector connecting 2 points. One of them being the origin, here in my case is H, and then the other point being the point on the polygon, in this case F. Okay, now before we do anything else, what we need to do is introduce our matrix multiplication. Right now it's not going to do anything because the matrix I'm multiplying by is the identity matrix, which applies no transformation. So the way I do this is in my algebra menu, I put my cursor in front of the word vector for each one of these. I'm going to say parentheses, matrix, and then make sure you have a space between matrix and vector and hit enter. Okay, so now look, vector H is now defined matrix times vector HF. And I'm going to do this for each one of my vectors here. So you should have matrix times a vector for every vector that we have put in. So since I put in 7 points, I'm going to have to do this 7 times. But once I have it, I have it. So there I have matrix times each vector. Okay, now what we're doing is we're setting up a way to visualize these transformations. Okay, so now that I've typed in matrix times my vector 7 times in my case, you can see that each one of these vectors is defined as a matrix times a vector. And so far nothing has happened, and that's because we are multiplying by our identity matrix. Later on we're going to change our identity matrix to something else, and it will then change our image. But to do this, I mean, if I did this now, it wouldn't work the way I want. So what I need to do now, which sounds counterintuitive at first, but I need to make the original polygon go away. Now the way I'm going to do this is by using in the algebra menu these colored circles on the left hand side. Make sure that your cursor is on the move tool so that you don't accidentally drop in some unintended vectors or points or something like that into the plane. And when I click these circles, notice that my points are starting to disappear. And I'm also going to make my polygon disappear as well. So now all I see are the vectors. Okay, now what we're going to do is redraw our polygon with points, and I'm going to add points to the tip of each vector. Now why do I have to do this? Because remember, my original points were defined as coordinates, but now if I look at my new points, so here's point I, which is the one I just added in. Point I is not defined as coordinates like the others were. It's defined by the vector u. So now this point, even though it's geometrically in the same place as my original point, is not defined by the coordinate xy. It's defined by what my vector u is doing. And so I'm going to add points to the tip of every vector. And now I'm going to go back to Polygon tool and connect my points just like I had in my original. And so now I have a polygon in which every point of this polygon is defined by a vector. And those vectors are defined using some sort of matrix multiplication. Okay, so now we are ready to do some transformations. All we're going to do to finish up this part of our project is we're going to hide our vectors so that you can't see those at all. And I'm going to go ahead and hide my points because I just want to see the polygon. And then I'm also going to turn my original polygon back on so that I can see what it looks like once I apply my transformation. Okay, so now we're going to start playing with different matrices to see what our transformations look like. So originally, what I'm doing here is I'm multiplying each vector by the identity matrix. And so when I do that, nothing changes. But if I change my matrix to have maybe, let's say, -1 in the first entry, when I apply that linear transformation, so I hit enter, whoa. Okay, so now the orange is our new polygon, the blue is the original. And notice what happened. I had some sort of reflection. In fact, when I multiply each vector by the matrix -1, 0, 0, 1, it applies a rotation about the y-axis. So let's play with some others. Let's try 1, 0, 0, -1, and let's see what happens there. Okay, so now I have a flip, but this time it wasn't around the y-axis, it was around the x-axis. Okay, so we used 1s in both of these cases. What if I do something like this? What if I multiply just everything by 2? What happens? Whoa, so I need to zoom out a little bit. Ah, look, it's the same image, but this time it doubled. And I think that makes sense because all my vectors now have just doubled in magnitude. Okay, so multiplying in a scalar, I think then, just scales the whole image. So if I multiply by 1/2, 1/2, I get an image scaled by 1/2. Okay, good. Now, what if we try something like this? So we're just kind of playing around. What if I say 2 in that entry and 1 in this entry? What happens? So if I zoom out a little bit, it looks like it's the same image, kind of, but it's just been stretched horizontally. Okay, so I think if I typed in -2, I think I have a pretty good idea what's going to happen. It's going to be a flip around the y-axis, and then it's also going to have this stretch. Yep, I think that works. All right, so I got another idea. What if I said 0, 1, 1, 0? So now I kind of take the identity matrix and I flip my first two columns. What's going to happen here? That's not quite as obvious, but I think if I put in the graph y equals x, maybe that clarifies what's going on. I have some sort of symmetry about the line y equals x. So in other words, the x and y coordinates swap positions, some sort of inverse mapping here. So this matrix here is a flip around the line y equals x. Alright, so I got another idea. Let's try this. Let's put 1s back in the main diagonal, so let's not flip it like we had. And let's make this entry a 3. What's going to happen? Whoa, okay, so I have the same orientation, but this is like some sort of skew. Let's make a smaller value, let's say 1/3, just to see what happens there. Okay, I'm taking the same image, but I'm kind of skewing it or shearing it in one direction. Okay, so I think now we've kind of got a good idea of how matrix multiplication can alter an image. Let's animate it. Okay, so GeoGebra is really good at this, and what we are going to do is we're going to use this slider tool, and I'm going to drop a slider down into my grid. My slider's name is P. Keep up with that, whatever your slider's name is. And I want to go from negative 2 pi to 2 pi on my slider. So I'm going to hit OK. There's my slider, and then with the move tool, I can just move that back and forth, and that's it, because nothing here is dependent upon what the value P is. Not yet, anyway. Alright, so now we're going to redefine matrix like this. Instead of doing constants, we're going to say cosine P, sine P, negative sine P, and cosine P. Now, before I hit enter, let me explain what's going on here. If I wrote my xy vectors in terms of polar coordinates, so that's like r cosine alpha, r sine alpha, and then I did matrix multiplication with this matrix here, the result with a trig identity is just cosine alpha plus p sine alpha plus p. So it just adds the angle. And what does that translate to? So now I'm going to hit enter, and as I toggle p around, it's just a rotation. So I can rotate my image now just by changing the angle using this transformation matrix. Cosine, sine, negative sine, cosine. And that's why I went from 0 to 2 pi. So I can go, it looks like I'm doing two complete circles here. So that's it. This is our illustration using GeoGebra. And I hope you find it interesting, and I hope you learn that linear transformations have a lot of use in the real world. If you have any questions on this, of course, you can let me know. You can either reach out to me or let me know in the comments. I'd be happy to help. I hope you learned something today, and thanks for watching.